honestly, long time no see. Andrew NG from Amir NP. I'm here at MIT. That's it. What is it? AI and the next computing platforms with Jensen Huang and Mark Zuckerberg. Wow, that's amazing. The Nvidia and Zuckerberg together. Machine learning course. What's up here? Machine learning course. Is an ad? No. By Fang plus ML engineer. I was an MIT educated neurosurgeon. Dude, you're a liar. We don't have a neurosurgeon at MIT. Now I'm unemployed and alone in mountains. You were wrong before and you are wrong now. Let's go, what else? This guy has acne problem. This guy, and I want, oh, this guy made it even to this YouTube channel of me. Not YouTube channel, my YouTube account. These are uninteresting subjects. This is just about me being a computer scientist. So let's go. Andrew NG, long time no see. Playlists. Where are we in the Andrew NG journey? I felt I don't need it anymore. Okay, 14 actually. Dude, let's finish it.
Long P of
What
x,
the fuck do you have to say? Finish it.
given the parameters, right? And then you take the derivative, set the derivative equals to 0, and you guys did this in problem set 1, right? And then you would find that phi j is equal to 1 over m
It's from Stanford Online. Go watch it there. Wow, Stanford has 6.6K subscribers. How much MIT has? That's a good question. It feels like people used to go to doctor's office and say, oh, this guy has like this amount of patients. How much he makes this and now is MIT. Woo! 881K, bitch. Stanford, you are no fucking. Maybe Stanford has just a Stanford account. Wait a second. So we have. Fuck off. Dude, fuck off. I don't want to search anything. Escape. MIT. Oof. OpenCourseWare has 5.28 million. That's called value. Very nice, very nice. Do they have any course about machine learning? They definitely have. Damn, they have so many courses. Dude, honestly, there is no reason to stay behind. You can learn whatever you want on internet. Let's see how many Stanford has. 1.93 million. Army officer, data scientist, and Miss USA. Wow. That's a scam. That's that sounds like a scam. Okay. And hot. And hot. Alright. What is this? What is this XIZJYY?
So if
I
only you
forgot.
knew
I
the values
totally
of the
forgot.
CIs, then you could use maximum likelihood estimates, and this is what you get. And this is pretty much the formulas. Actually, these two are exactly the formulas we had for Gaussian discrete analysis, except we've replaced Y with Z. Right? And then there's some other formula for sigma that's written in the lecture notes, but I won't write down here. Okay? But the reason we can't use these formulas is we don't actually know what are the values of Z. So what we will do in the EM algorithm is two steps. In the first step, we will guess the value of the z's,
Expectation
and in the second
maximization.
step, we will
EM.
use these equations using the values of the z's we just guessed. So let me. So sometimes in machine learning, sometimes we call this a bootstrap procedure, where you guess something, they run an algorithm, you're using your guesses, and then you update your guesses, and then run the algorithm again. Let me make that concrete by writing this down. So the EM algorithm has two steps. The E step, also called the expectation step, is set Wij
I remember something about it from my
So Wij
information and
is
inference
going
class.
to be the probability that Zi is equal to j, okay? Given all the parameters. And much as we did with generative learning algorithms, right? With generative learning algorithms, we use Bayes' rule to estimate the probability of y given x. And so to compute this, you use a similar Bayes' rule type of calculation. And so this would be right? Where, for example, this term here, P of xi given zi equals j, this would be a Gaussian density, right? This comes from a Gaussian density with mean mu j and covariance sigma j, right? And so this term here would be 1 over, 2 pi to the n over 2 sigma j, so 1/2 e to the negative 1/2. Right. And then this term here, I guess this would be phi j. That's just a Bernoulli probability. Remember, z is multinomial, right? So z is multinomial.
We should have a
with parameters
session
phi.
outside.
So I guess the
Outside
parameters phi
weather
from
is so
multinomial
nice.
distribution tell you
I will
what's
do
the
that. I
chance
will
of
do
z
that.
being 1, 2, 3, 4, and so on up to k.
Boston
And so the
sky
chance of
is
zi being
like
equal to k is just
so beautiful.
the chance of zi being equal to j
So
is just
fucking
phi j,
beautiful.
right? It's just read it off one of the
Massive
parameters
cloud.
of the multinomial probability for,
I don't know. There
for
is
the odds of z being different
part that
values.
is darker
And so,
inside the
and
massive
similarly, the
white
terms
part,
of denominator,
and you can
this
see
term
blue.
here is from
When the sky
Gaussian,
is blue, it's
and that second
super
term is from
clean.
the multinomial probability that you have for z. And so that's how you plug in all of these numbers and use Bayes' rule, use this equation to compute, given the position of all these Gaussians, what is the chance of Wij taking on a certain value? Okay. And so to make this really
So
concrete,
this is a tree.
you remember how, I guess, ones and zeros are the other way.
Crazy.
If you
Ow,
were to look at these, if
Do you
were to
see
scan from
that?
right to left,
Do you see
remember
this
how,
part?
you get
This
a
part?
sigmoid function, right? Or the
is
sigmoid
my
can be this
finger,
way
by
or
the
this way, right, depending on the sign. I guess if
This
these are positive
part-
examples, these are negatives, you have a sigmoid function like this.
crazy.
And so
It's like a
Wij
city.
is just
Like
the
clouds
height
are buildings of the
this sigmoid.
city.
It's just a
It
chance
has depth to it.
of,
It's not. First
each of
time
these
I'm
examples
seeing such a
being
cloud.
coming from either the
Is it a storm or
z equals
something?
1 or z
And then
equals
look at
0,
the
and
blue.
then you store all of these numbers in the variables
so
Wij.
pretty.
Okay, so Wij
And,
is just compute the posterior chance of this
trees.
this example coming from
Actually,
the left
this is
Gaussian
the
versus
best
right
time
Gaussian,
of the
you
year.
just store that,
I
in
changed
the
my mind. I
Wij.
thought May is the May is the best month of the year because all
So-
the amazing fruits and everything good. It's just the start of it, and you get excited.
That's the ESEP.
But to be honest, this part of the year we have
and you
even
compute
less
the
rain
WIJ for every
here
single
because in
training
May
zone.
there is some shitty thing around Boston that
Yes,
every
and-
weekend we have rain. Rain happens
Yes,
every weekend,
yeah.
and it happens like for 4 or 5 weeks. So weekends are fucked. Here you can see that.
Sorry,
You
is
can
this
see
what-
that. Here is just now we are in August, right? Like August 7, 8,
Oh, this
whatever.
one. Sorry. Yes.
Weather is not super hot.
Yes.
June was okay. Late July and August, early August are actually very cool. The weather is super nice. You can see that the trees are very green, and sun is not burning
And then in
you.
the M-STEP, what we're going to do
You don't
is
need to
use
like. It's
the
not
formulas
very
we have
hot outside. You can
for
wear a
maximum
t-shirt
likelihood
and it's
estimation.
chill. It's not
And I want you
cold,
to compare
no,
these
not-
with the equations I had
not
above.
hot, not cold. It's perfect temperature. It's really good. What is this cloud? Look at this. Do you see these different shades of gray here? It's just, it has depth to it.
Well, hope you can see. But so these equations are
We have a
lot like
big
the equations
white
above,
cloud,
except that,
which is at the
instead of
back, and there are some
indicators
other
in R
clouds.
equals J, we
Oh,
replaced
that's
with,
it. Like we
W
have a big white
I J,
cloud at
which,
the
by the way,
end
is the expected value.
in the background.
Of this
Well, the
indicator
background of background is the blue sky, right? And then we have a layer of
Because
big
the expected value
spread
of the indicator
white
function is just
cloud.
equal to the
Then there are
probability of that
some
being
clouds
true.
which are closer to us, but the shade of this big
and
cloud
then
on
there's the
them
formula for
makes
sigma
them
j
look
as well.
darker.
That's you can get
This
from
is
the lecture notes, but I
crazy.
won't
How
do
is
that.
the weather? Let me check how the weather is.
So, one intuition of
One
this
intuition
mixture of
of
Gauss's algorithm is that it's a little bit like k-means, but with soft assignment. So in k-means, in the first step, we will take each point and just
oh,
assign
it was
to
like
one
the
of the
K-mean algorithm.
classes.
That's an interesting algorithm, by the way. So we had a lot of points. We wanted to choose classify or cluster to K groups, right? And then we want to choose what is the mean of each those centroids or whatever. So we start from K different points in the city points on the plane or in the space. Then we choose all the data points that are closer to those mean and compute the mean of these points and update our mean to these new points and repeat this procedure. Is that it? That's a very interesting algorithm. Can we have a radius for each of them? Oh, and then radius, it is the sigma of the Gaussian noise. Okay, now I totally remember. All right. Maybe I should put it here. It's something like that, not much more complicated. Damn. Weather is so nice. Let's see. Oh, by the way, Iran won. Iran fucking won. Hadi Sarawi. Congrats to all of my people from Amol, my hometown. We got the first gold medal. That was amazing. I just so many things happen at the same time. I forget. Oh my god, it was amazing. Yeah, good job. All their his family were so happy at home. That was cool. So we have this. Oh, this is from wrestling. All right, and then Hadi Sarawi is not from Sari. He's from Amol. Interesting point. What else do you want to say? Congrats. I should post a story, by the way, about it. David Blaine put his tongue out. Hadi Hadi Chupan was. Dude, it's not. Alright. Oh, it's here. Olympic 2020, he got bronze. Asian Games, he got gold. 2021, 2022, 2021, he got World Champ gold medal. 2022 and 2023, he got bronze. And 2020 World Cup. What is the difference between World Cup and World Champ? He got bronze, and then a lot of other. Okay, now he has a gold Olympic. This, I think that is the most important one in my, like, it was his first Olympic medal. Good job, man. Congrats. When is this? Oh, these are old. Oh, this is the pin. Yeah, he was wearing blue. Dude, very good job. How can I post this to Olympic. He did a half-ass backflip. That was funny though, and he was like the moment Iran and Spain had. They were playing football in World Cup, and at last moment one of Iranian players just tries to throw the ball from outside. He does it forward, but it doesn't work. It was so funny. It's like these moments that it's very you are very emotional as a person, because like it's somebody from your country winning, or in that case it was losing. But they do a flip or backflip and they can't make it. And the whole emotional state changes and you want to laugh at them. It's very funny. It is not this though. Oh, it is this. He was wearing gray. That's actually good. Okay guys, I'm getting distracted, but this one is really important. It was first gold medal of Iran, by the way. Okay. Hopefully one day we have somebody from Losem who can win a gold medal for us. Perfect. Actually, there is another. Oh, that is for freestyle, right? Is it called freestyle? I don't know. Zare also from Omol. Bro, Omol is killing it. Okay. Let's get back to our K-mean.
Right, and it was a little bit closer to the red cluster centroid than the blue cluster centroid. We would just assign it to the red cluster centroid.
Centroid, so I remember.
K-means would just make what's called a hard assignment, meaning, whatever cluster centroid is closer to, we just assign it 100% to that set cluster centroid.
Yeah.
So
it's not that?
EM is,
because it is Gaussian. Yeah, because it is Gaussian, it may not be 100% to the closest. I see. Very nice, beautiful. So we need to have weights for each K of the means. I completely agree.
EM implements a softer way of assigning points to the different
Good.
cluster
Okay, I got
centroids,
the whole
because
idea.
instead of just picking
The
a one
details, I
closest
don't care.
Gaussian center and assigning it there, it uses these probabilities and gives it a weighting in terms of how much is assigned to Gaussian 1 versus Gaussian 2. And then second, it updates the means accordingly, right? Sum over all the xi's to the extent they're assigned to that cluster centroid divided by the number of examples assigned to that cluster centroid. Okay, so that's one intuition between EM and k-means. And then the second, when you run this algorithm, it turns out that this algorithm will converge with some caveats I'll get to later, this will find a pretty decent estimate of the parameters, of say fitting a mixture of two Gaussians model. Okay.
He's a cool professor. I don't know. I have
this is,
the feeling that he's a nice
and so
person.
if you are given a data set of, say, airplane engines, you can run this algorithm, fit a mixture of two Gaussians, and then when a new airplane engine goes off the assembly line,
actually, I think he's the
so after you're fitting the
leader
k-means
of
algorithm,
Google
you now have after fitting EM algorithm, you now have a joint density for P of x comma z. And so the density for x is just sum over all the values of z of P of x comma z, right? And so
he's British American.
And so a mixture of Gaussians can fit distributions that look like this. It can fit distributions that look like this. Right. These are both mixtures of two Gaussians. So this gives you a very rich family of models to fit very complicated distributions. And now that, right, and you can also fit, I don't know, something like this. Right? So this is a mixture of two Gaussians. I guess one thin, narrow Gaussian here and one much wider, fatter Gaussian. So a mixture of two Gaussians can actually fit a lot of different things. Can fit a lot, and a mixture of more than two Gaussians can fit even richer models. And so
like
by doing
so
this,
much
you can now model P of x for many complicated densities, including this one.
That's amazing.
This example I had just now.
This
will allow you to fit a probability density function that puts a lot of probability mass on a region that looks like this. And so when you have a new example,
actually, I like my
current
current project too.
P of x
this is really
large,
good. This is something
say,
we are thinking
this
about
okay.
it. I made a
And
model.
we
can try what's going on. It's actually I like them more. I may not like working with mechanical shit, but on social platforms you can see how human beings.
I kind of just wrote down this algorithm with a little bit of a hand-wavy explanation for how it's derived, right? So I kind of said, if only you knew the values of z and just use maximum likelihood estimation, so let's guess the values of z and then plug that into the formulas for maximum likelihood estimation. It turns out that hand-wavy explanation works in the particular case of EM for mixtures of Gaussians, but that there is a more formal way of deriving the EM algorithm that shows that this is a maximum likelihood estimation algorithm and that it converges at least the local optimum. And in particular, what we'll do is show that if your go is given a model P of x, z parameterized by theta, if your go is to maximize P of x, right? Excuse me. Right. So this is what maximum likelihood is supposed to do. That EM is exactly trying to do that. Okay. So I'll go on in a minute to present this more general derivation, the full, more rigorous derivation of the EM algorithm that doesn't rely on this hand-wavy argument of let's guess the z's and use maximum likelihood with the guess value. So I'll do the rigorous derivation of EM in a minute. But before I do that, let me just pause and check if there are any questions.
I hate this. Honestly, give me some money, I can buy a new tripod. Actually, this is what. Fuck.
Yeah. Maybe, let's see. Maybe it'll help to not think of them as weights. Yeah. I think this is actually the weighting you assign to a certain Gaussian. So that's one intuition, hence weights. But Let me think. What's a good way to explain this? So one way to think of this as Wij is how much xi is assigned to, you know, to the mu j Gaussian. Right? So Wij is the strength of how strongly you want to assign that training example xi to that cluster or to that particular Gaussian. And so this is a number between 0 and 1, right? And the strength of all the assignments, and every point is assigned with a total strength equal to 1, because all these properties must sum up to 1. And so we're going to take this point and assign it, you know, 0.8 to more close Gaussian and 0.2 to more distant Gaussian. And this is our guess for, you know, well, there's an 80% chance it came from that Gaussian, 20% chance it came from a second Gaussian. Does this make sense?
Have you already just randomized these, or is this determined as these? That's my confusion.
Oh, I see. So let's see. So when you're running the EM algorithm,
Dude,
you
I
never
love
know
to
what
be
are
an
the true
engineer.
values of
I love it.
Right? You're given a data set, so you
Just
only
they
tell
don't
the
let us
axis.
be engineers.
And
Who
far as
doesn't
we
let you?
know,
I will.
these airplane engines
No,
were
it's
generated
just a
off,
limiting
you know, two
mindset.
different
I
Gaussians.
wanna
Maybe
be
there are
one.
two separate
Just
assembly
give me a
processes,
fucking
you know,
job. That's
one
what it
from
is. Give me an internship, and
one
I.
from plant number
Okay,
one,
there are
one
a
from
lot
plant number
of
two, and maybe
nuances. Like for example, even if you have a good idea, I was talking to Ehsan. Like there are different teams, and they are fighting for their agenda. Like you have multiple teams. They want to implement their own ideas on this platform. And you sometimes you have a lot of ideas, they don't give it to you.
they actually operate a little bit
opportunity.
differently, but by the time they merge onto one, but by the time the two suppliers of aircraft engines get to you, they've been mixed together, and so you can't tell anymore which aircraft engine came from plant 1 and which aircraft engine came from plant 2. And you don't even know if there are two plants, right? You just see the stream of aircraft engines, you're hypothesizing that there are two types.
That is
And
so
every-
beautiful that you can, I don't know, it's all the time, but we can talk about the things within phenomena like learning, everything, we can talk about them with math. Even like game theory, it may not work, but still gives us something. I'm really happy that we have mathematics. Even if we cannot solve the problem, just the part that we can come up with a mathematics. Okay, this part is just doesn't make sense. At the end of the day, it's all about the results. But it's just it's just nice to be able to talk about things with mathematics.
Iteration of EM,
I know.
you're taking each aircraft engine and guessing. You know, for this one, I think there's 8% chance it came from process 1 and 20% chance it came from process 2. So that's the E step. And then in the M step, you look at all the engines that you're kind of guessing were generated by process 1, and you update your Gaussian to be a better model for all of the things that you kind of think were generated by process 1. And if
However, I usually start modeling things using probability theory or analysis or game theory, like other areas of math, like topology or algebra. Okay, I have seen some applications of algebra in like coding, but those areas in general, it's not my go-to things. Either I need to learn more topology, maybe that's just gives us better understanding. But like topology is super abstract. What are the applications of topology? Applied topology. Data analysis, ha 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 ha. What was that? Like there are like fucking coolest stuff about mathematics, right? Topology. You only see them. I only saw them in university, and I was like, where? Okay, they have a lot of application in physics for sure, but in engineering, Well, okay, there was a guy, one of the MIT's ex-professors, what was his name? Suprit. Suprit used to do a lot of topology stuff. So, okay, yeah, they have use in data science. Yeah. Oh, it was not topology, by the way. It was geometry. It was manifolds. Manifolds is again more like functions and you know, complex functions. So topology, I never know. Applied topology. Very nice. Who is this guy? Such a gentleman. Manifolds, complexes. Yeah, this stuff may have application in physics. I don't know, in engineer. Cool. Okay.
There's something that you're absolutely sure came from process one, then it has a weight of 1, close to 1 in this. But you think there was something that, you know, at a 10% chance coming from process one, then that example is given a lower weight and how you update the mean for that Gaussian. Make sense? All right, cool. All right. So, it's about 33 minutes. Yeah. Okay, cool. All right. But I still remember when I was an undergrad doing a summer internship at AT&T Bell Labs. And then someone, a few offices down, had learned about EM for the mixture of Gaussians for the first time. He was running along his computer. And he was going around to every single office saying, oh my God, you got to check this out. This is unbelievable. Look at what this algorithm can do for fitting mixtures of Gaussians. So I mean, it shows you, those are the type of people I hang out with. Yeah. All right. So in order to derive, so just slightly hand-wavy arguments, like, oh, let's guess the values of the z's, let's just have these weights and plug them into maximum likelihood. What I'd like to do is give a more rigorous derivation for why EM algorithm is a reasonable algorithm and why it's a maximum likelihood estimation algorithm and why we can expect it to converge. And it turns out that rather than just proving that this is a sound algorithm, what we'll see on Wednesday is that this view of EM allows us to derive EM in a more correct way for other models as well, the mixtures of Gaussians. On Wednesday, we'll talk about a model called factor analysis that lets you model Gaussians in extremely high dimensional spaces, where if you have 1,000 dimensional data but only 30 examples, how do you fit a Gaussian into that? So we'll talk about that on Wednesday. And it turns out this derivation of EM we're going to go through now is crucial for applying EM accurately in problems like that. Okay, so in order to lead up to that derivation, let me describe Jensen's inequality. So let f be a convex function. To do EM, we're actually going to need concave functions, so it'll be all minus of everything, but we'll get to that in a second. But so a convex function
expected of f of x is
means the second derivative
greater than or
is
equal
greater than 0, or in
f
other words,
of
simple like
expected
that,
of
right? So that's a convex function. Let x be a random variable. Then f of the expected value of x is less than or equal to the expected value of x. Okay, now maybe here's an example, right? So here's a let's see, there's the function f of x, and let's say that these are the values 1, 2, 3, 4, 5, and suppose that x is equal to 1
How
with
far can I
probability
go?
1/2 and is equal to 5 with probability 1/2, right? Just for illustration. Then
I cannot go more.
here is f of 1.
Okay, first of all, my hand is not long enough for going further.
Here is f of
Well, I have some
5.
space.
Here is f of 3, and f of 3 is f of the expected value of x, right? Because so the expected value of x, and
Well,
sometimes I
it's
write
not
this without
about
the
that.
square brackets, right? Is the
It's
average
about
of x
my
is equal to
hand.
3. And so the expected value, excuse me,
Okay.
f of the expected value of
I
x
feel the
is equal
table
to this
without
value,
this to
whereas the
collapse. So I'm not
expected
gonna do
value
that.
of f of x is the mean of f of 1 and f of 5. Right? So the expected value of f of x has a 50% chance of being f of 1 and a 50% chance of being f of 5. And so the expected value of f of x is equal to this value in the middle. It's really take these two, right? Take this value and take the mean. So it's this value up here. And this value is the expected value of f of x. Okay? And so in this example, the expected value of f of x is greater than f of the expected value of x, right? As predicted by Jensen's inequality. I'm going to just draw one illustration that may or may not help. Some of my friends like it. I sometimes use it, but if it's confusing, then don't worry about it. But
The Armenian guy looked much bigger. By the way, I don't know how are they in the same weight class? That the Armenian guy was even taller and puffier. The only reasoning is that his body is just fat or some less dense version of muscle or bone density of the Iranian guy was high, bro. Okay, you play.
it turns out that if you draw a line that connects these two, then the midpoint of this line is the height of f of expected value of x, right? So the height of this, so given these 2 points, this point and this point, if you draw this line, it's called a chord, then the height of this point is expected value of f of x. And this point is f of the expected value of x, right? And in any convex function, really take any convex function, that's also a convex function. If you draw any chord, that green point is always higher, right, than that green point, which is another way of seeing why Jensen's inequality holds true. Okay, if this visualization doesn't help, don't worry about it. But just actually, what a lot of my friends do is we keep on forgetting which direction Jensen's inequality goes. Like when we're using this, let's not grade that. So a lot of my friends, when we don't remember, we draw this picture and draw that chord, and then we quickly figure out which way the inequality goes. All right, so. One addendum. Further, if f is strictly greater than 0, and so if this is the case, we say f is strictly convex. Then.
Damn, I want to do wrestling. Bro, if their body looks like that, do you think wrestlers have such huge bodies because they do like bodybuilding as a side hustle, like side sport, or it's just doing the wrestling make them so big? Because like you look at the boxer or striker, they don't look big because they box. That doesn't improve your muscle. But if you're wrestling, if that makes you big and you learn how to wrestle, actually I like to do wrestling. Actually, my friend El says that you need to start very early, but
Okay.
something I cannot.
So let's see. A straight line is also convex.
Something I
function,
cannot.
right? So this is a convex function.
But
This is a convex function.
who
This is a
cares?
convex function.
I
Turns
mean,
out a
learning
straight
some
line that's
techniques
also
is
a
also
convex
good.
function. But so
Never-
this
it's never
addendum
late,
is saying that if f is a strictly
even for
convex
wrestling.
function, meaning
I wanna go
basically
to
it's not a
Olympics.
straight line, right? And
To watch
a
it,
bit
though.
more than it's not a straight line. But if the curvature, if it's always bending up, then the only way for the left and right hand sides to be equal is if x is a constant, meaning it's a random variable that always takes on the same value.
Yeah, if it is
So
fine,
Jensen's
it's
equality says
equality.
that, you know, left hand side is got to be the same as right hand side. Sorry, I think I reversed the order of these two for that equation, but it doesn't matter, right? But so Jensen's equality says left hand side is always less than or equal to the right hand side, and the only way it's equal is if x, you know, is a random variable that always takes on the same value. Okay. Yeah.
Let me text my family because they called me. Perfect! Let's go! Dude, I'm gonna finish this. We are jinxed on this Jensen inequality. K-means was
Yeah,
so
so it
beautiful.
turns out what if
K-mean
none
was
of one is equal to
smart,
none of us?
beautiful.
It turns
I
out
loved
those
it. Jensen,
very-
I
so let's
already
see.
know.
So one way that
So
should
let's
happen would be
watch
if
it
the
for the
function-
next 20 minutes,
like
and we are
that.
going to
And then if you
the
take
last
the
quarter of
take the
this
unit
fucking
step.
show. Session 15. Oh, actually, session 15 even is not in the last quarter. Lesson 15 is the
then
third
this is
quarter.
If,
of the show.
if you
Oh,
have a flat
okay.
part here,
Anyways, we
then
will
the function
finish
is not
it.
strictly convex, and so it's still.
I got
less
so
than equal to,
involved
but it's
with
not
the all
really
other
can't be equal
projects,
to
I
x as well.
forgot to finish this.
So
And other projects had
and we
coding
use this,
involved in it.
in a little bit. We'll
So I
actually
didn't
end up
feel
using
like
this,
doing coding sessions anymore. By the way,
again,
I
for the
learned
strict
it.
probabilistic, you know, those of you that
Fuck.
don't know,
I learned
take
Python.
classes
I
in
know how to
advanced
do
probability,
Python now.
the technical way of saying x is a
I
constant
know how to
is
do
x
Python
is,
now. That's crazy.
equals to ex.
Their X
with
rest
probability
is
one.
extra. I don't know. Learn a library. Work. They are just ChatGPT stuff.
You know what? I think for all practical human purposes, you
Any
do not
fucking company who wants to interview me for this kind of stuff, they are stupid.
need to worry about this. But I think if you take a class in measure theory, the professor in measure theory will be happy if you say this and you say x is a constant, right? Maybe none of you are. Okay, yes, don't worry about it. Oh yes, okay. Now, just one more addendum to this is that the form of Jensen's equality we're going to use is actually a form for a concave function. So instead of convex, I'm going to say concave. And so, you know, a concave function is just the negative of a convex function, right? If you take a convex function and take the negative of that, it becomes concave. And so the whole thing works with everything flipped around the other way. Yeah, yep. And so F is strictly concave. Okay. So the form of Jensen's equality we're going to use is actually the concave form of Jensen's equality, and we're actually going to apply it to the log function. So the log function, right? Log x looks like this, and so that's a concave function. And so the inequality we'll use will be in this direction that I have in orange. All right. So here's the density estimation problem. Meaning density estimation means you want to estimate P of x, right? So we have a model for P of x comma z with parameters theta. And so, you know, instead of writing out mu sigma and phi, like we did for the mixture of Gaussians, I'm just going to capture all the parameters you have, whatever your parameters are, I'm just going to capture them in one variable, theta. And you only observe x. So your training set looks like that. So the log likelihood of the parameters theta is equal to sum over your training examples log P of xi parameterized by theta. And this in turn is log of sum over z P of xi zi parameterized by theta, right? Because P of x, you know, is just taking the joint distribution and summing out, marginalizing out zi. Okay.
Yeah, I have to add 3
And
plots
so what we want
to the plots we have for,
is
for the
maximum likely
Gaussian.
estimation, which is to find the value of theta
Forget about it. Now let's
that
focus on
maximizes
this.
this log likelihood. And what we'll like, what
We
we'll
have
like
20
to do
minutes
is derive
to
an
wait.
EM algorithm.
Okay, I
derive
want
an
to
algorithm,
focus on
which will
this.
turn
I
out
don't
to
want to
be
think
EM
about
algorithm.
Gaussian now.
As
We
an
will think
iterative
about
algorithm
Gaussian whenever we
for
want to
finding
start Gaussian.
the
Now
maximum
it's just
likelihood
Andrew and
estimates
you. I want to
of the parameter
listen.
state.
I want to listen to your story, Andrew. Tell us about Jensen inequality. Yeah, Jensen.
So
Yes,
let me draw a
plot the
picture I'd like
x-axis.
you to keep in mind.
Don't
as we
remind me
go
of
through
the
math,
Gaussian
which
plot,
is,
though.
you know, the horizontal axis
So
is a
it's
space of
concave,
possible values
it's
of parameters
theta,
theta.
parameter,
And so there's some function L of theta
L of theta,
that you're trying to maximize.
which is the loss function.
This way. And so what EN does is, let's say you initialize theta at some value, you know, maybe randomly
Stable
initialize.
equilibrium and
Um,
unstable.
Similar to the
Here,
Kidneys
here,
plus
and an
syndrome, which is you
unstable
randomly
equilibrium.
initialize your mu's for the
Yes.
mixture of Gaussians. What the EM algorithm does is in the
You're
E step,
going, or
we're
even
going
this
to
way.
construct a lower bound,
Wow.
shown in green here.
I always had the thought that Nash equilibriums that are stable equilibriums of a game are more interesting. They are the ones that happen. But even then, we don't know. I don't think we have like one unique stable Nash equilibrium. By the way, what does stable mean? Because Nash by itself is equilibrium. What is an stable equilibrium? Stable equilibrium is that if we deviate from an equilibrium point with a noise, we get back to the equilibrium, right? Even stable equilibriums are not fully equilibrium. Even if you look at the what is it called? Pendulum, right? So we have a stable equilibrium at the bottom, which almost every point we leave it, it will end up at this lowest point. But if you exactly put it at the highest point, which is an unstable equilibrium, still it is an equilibrium, it doesn't go there. So, by the way, even look at the curve like W, right? The 2 points under the points that keep W on the ground, those are stable equilibriums if we leave a wheel there, right? So those are stable equilibriums, but obviously they are not unique. So now in a game theory, so we can't expect where we have a unique Nash equilibrium that is stable. I don't exactly know what is a stable Nash equilibrium, by the way, but it cannot be unique. And then we can have partition of the space, of the action space, that in a dynamic setting of the game, once we repeat the game, where they will end up. Some of them may not even converge, some of them may converge, right? Yeah, actually we may not even converge for some starting points. So let's look at this. It's just so much distraction from the topic right now, but it's something I want to talk about it for a long time. I wanted to think about it, but fuck that. I'm not gonna read papers about it. Maybe one day I talked with Andy and he tells me, okay, there are some topics on it, but we can ask ChatGPT, by the way. Yeah, the most amount of investment is ChatGPT I can do. So what I was thinking is, like, let's assume we have two players, Alice and Bob. So we have Alice and we have Bob, and he has A1 as fuck Alice and Bob. I hate these names. So A1 is the action set of player 1. Player 2 is A2, and this is like A1 to A and B. Okay, actually now I think Alice and Bob is a good option. People thought about these names. So Alice has options A1 to AM. Bob has actions B1 to BN, right? And we want to say there is a game. We have a utility of Alice, which is a function of A and B, their actions, and we have a utility for Bob, which is an function of A and B, right? Then we say, what is it? Okay, what is the definition of Nash? Nash says UA of if A star and B star are Nash equilibrium, UA star and B star will be greater than any UA where we change A but B star stays B star, and the same for Bob. Bob doesn't want to change his action. If Alice doesn't change her action. Well, spoiler offer, Alice was trans and she changed to a guy. So Alice, we also use his pronouns for Alice, but he didn't change his name. And Bob was gay. Bob was gay. Alice and Bob now are a gay couple. That's it. They used Bob was straight before. Alice was a lady before. They used to be a straight couple. Now they changed. Everything works. We have words for all of them and pronouns. All right, so I'm using his for everybody. Now we are saying, okay, now what is the strategy of it? Okay, this is something I am doing on my own. This is my curiosity of what is going to happen is that let's do the time version. Function of time. Add element of time plus, and what I want to say is that Alice decides for his action this way. Updating action. Rule is that Alice AT plus 1, which is action of Alice at time t plus 1, will be argmax. Alice asked herself, what should I do if Bob keeps doing the same action he did before? What should I do now to make my action? So UA on A and B, BT though. We are maximizing on A. So Alice says, let's assume Bob takes the action he did last time at time t. What will be my best response to it, right? And the same for Bob. Bob says, I wanna take the best response to Alice's action at the previous time. So do you think this set of thing converges? Well, what is converge? If the action space is discrete, convergence means just turning into a constant sequence. But if it is continuous, it means convergence of a real sequence of real numbers, right? Obviously, if starting point, okay, now how about A0 and B0 partitioning the space, right? It seems it depends heavily on where we start. Not heavily, but yeah. So if we start from a Nash equilibrium, if A0, B0 is a Nash equilibrium, we will stay there, right? We stay there. But what if I'm curious to know what's going on to happen to first of all, two cases. Hoteling problem. Let's see what happens in the hoteling problem. Right? So we have this line, and Walgreen and CVS are deciding, and people are distributed uniformly 1 over L. This length is L, and CVS and Walgreens are deciding where to locate themselves. The thing is that they should put themselves next to each other, because whoever is closest to CVS goes for CVS. So this part of the population will go CVS, and this part of the population go for Walgreens. And you can see that if Walgreens moves closer to CVS, they get more customers, and if CVS moves closer to Walgreens, they also will have more customers. So therefore they should be on each other, so that both of them will get half of the population. So any x and x is a equilibrium? No, not any x and x is a equilibrium. So it should be x and x, right? But assume CVS is here. If CVS is as x, what is the best response of Walgreens? This is x. And x is less than 1/2, right? So I will choose x plus epsilon. And if CVS is x, which is greater than 1/2, I will try to be, I want to get the bigger portion of the line, so I will be on the left side of the CVS, but I will be very close to it, so that the people between us, I can get half of it. I always get half of the people. The point is that I always get half of the people that there are between us, right? And there is another important point in this line is the midpoint of the line. Whoever is, like wherever CVS is, I want to be to the same side of CVS as Walgreens, but closer to the midpoint. So I have half of the population plus the epsilon over 2 of the population between us. The only thing that it works the best is that CVS is located at the middle of the point. Then we get both half. So if it's x, CVS is x greater than 1/2, then BR for Walgreens will be x minus epsilon, right? If x equals 1/2, then best response is 1/2. And you can see now, the best, once x is less than 1/2, but Nash equilibrium is a point that you are best responding to the best response. So if Walgreens is x plus epsilon, which is still less than 1/2. CVS will be x plus epsilon, which will be plus 2 epsilon. And which is not an equilibrium, right? X is not equal to x plus 2 epsilon. So the only Nash equilibrium is 1/2 and 1/2. And you can see actually that this is a game that every point is converging to the middle ground, right? So CVS is x less than 1/2, right? A0 is x less than 1/2, and B0, let's assume, is y less than 1/2. What is going to happen? Let's assume x is less than y less than 1/2, right? What will Walgreen do? Okay, then A1 will be y plus epsilon, and B1 will be x plus epsilon. Actually, Walgreen turns out to be more greedy and goes towards left. Interesting. So now they switch actually. Well, very interesting. Now they are not converging even. So we have x, we have the line. Actually, I want to plot this. And see what happens. This is so fucking interesting. And epsilon can be anything as long as it doesn't change. Epsilon can be anything as long as it doesn't change your position to the middle point or the difference between your place and his place. Well, that would be Nash equilibrium. If you wanna consider the whole hierarchy of belief, it will end up in Nash equilibrium. But if you just assume that each person is taking best action to the other person at each previous time step, that wouldn't be Nash equilibrium necessarily. So we are here, it is 1/2. We have CVS here. We have Walgreens here. Then next year they end up here. It's actually interesting. Okay, they end up here because CVS goes x plus epsilon, and which is here, a bit bigger, and Walgreens goes here, a bit to the right. So they're switching, but by an epsilon factor. And then you can see that this epsilon can be very small, by the way, which should be very small. They're almost on the same thing. Then they switch again next year because of the same reason, right? So they're shifting to the right a bit. So this will be it, and this will be. So they're shifting towards 1/2, but they should never reach 1/2 by the method I mentioned. It just takes for infinity for them to get to 1/2. If I define epsilon anything less than minimum of x 1/2 minus x y minus x and 1/2 minus y, right? Something like that. So it's interesting to look at it at x, y. What are other games that are in a continuous space? So this is it. Not x. Yeah, a, t, b, t, a and b. A, b. So we started x and y, which y was bigger. And this is the line for y equals x. This is the line for y equals x. This is 1, this is 1. So we started here. And 1/2 is here, by the way. One half, right? So we started at x, and then here is y, and here's our first point. Maybe I should write it down. Then we kind of switch. We take its reflection with respect to the first quadrant. What is it called? The line that makes it in half, 45 degrees. We come here, but we have also an epsilon edge, so we come here, kind of. Right, we come here. Then, but remember, epsilon is always keeping the shape below 1/2. Yeah, epsilon is designed in a way that it's always below 1/2 and less than their distance. So here, instead of minus y, is epsilon less than minus max. If you say epsilon t plus 1, max of at and bt. So we never get to and also y and x, let's say bt minus yt, 80. Right? So it will be a curve like this, just almost. They are going toward 1/2. Actually, they are not going toward 1/2, for instance. We should just stay here. They should stay here, to be honest. But we we have some epsilon, so in a sense they are going ahead. I don't know. This part requires some mathematical rigor, but we are kind of here towards 1/2 maybe, but we'll never get there. So what is this line, by the way? kind of know what these lines are, right? This is a line that is connecting x and y to 1/2 and 1/2, and this is a line that is connecting y and x to 1/2 and 1/2. So if I want to build it over t, for example, for at, a is at x at the beginning, and then we have y, and at the infinite we have 1/2, but this line, this is not linear, by the way, this is this depends on our epsilon update rule, because our epsilon should be something positive. And then this is the line, and like these are the two envelopes, and what we are doing is just as x we are bing between these two curves. The same for y. So all points here kind of converge. I'm not 100% satisfied. What is this epsilon? Because we are not defining a minimum for epsilon. Epsilon can be very small and close, which makes the problem not well defined. I think the problem is not well defined. But it's going to 1/2. So this square here, it goes to 1/2 easily. The square above it also goes to 1/2 and 1/2 easily. What about if x is less than 1/2, y is greater than 1/2? X, yeah, the problem is not well defined, so I'm not being very rigorous right here. And we have 0, 1, and we have 1/2 in the middle. So next time a1 again will be x plus epsilon. This time b1 just will be y minus epsilon instead of being so if the y is here, xy, we go y minus epsilon, which is similar. It's just again we need to come here, y minus epsilon and x plus epsilon. So it's here, we just add to x, the y is a bit bigger, and right, this point is reflected toward the half quadrant's middle line, and we just decrease the x, increase the y, and then they also will converge to that shape. Okay, so all of them are going towards the middle point. Not rigorous mathematics again. Interesting. If we say epsilon is just 0, what will happen? They won't go towards that place. They won't go towards that place, and they just switch between the 2 points. So it is very probable in a discrete game that they oscillate all the time. Yeah, actually very obvious. You just consider a matching game, right? Consider a matching game, Alice and Bob. So this stable thing may not be very interesting, to be honest. I don't know, wait a second, what is an unstable thing? So if it is like 0 and 1 for Alice and Bob, and they have to match, and if they match they get 1, and if they don't match they get 0. Well, if they are lucky and their starting point, both of them are 1 on 1 or 0 or 0, they will stay there forever. But if they start from this point where Alice is taking 1 and Bob is taking 0, They always switch between these two cells and they will never converge. This is actually the beauty of hierarchy of beliefs. Very interesting. I'm so happy I finally take a look at this paper. But okay, this is just about Nash. What about the case that, by the way, I will make sure that we finish Andrew Ng this time. What was I thinking? So again, back to stable, being a Nash equilibrium, being a stable. Well, these are not stable. None of these Nash equilibriums in this matching game are stable because once I move, deviate even in one action. So, okay, I don't even care anymore about the stability definition in an equilibrium because the most simple form of perturbation for an action profile is one person keeping it the same, the other person changing the action, and it's not stable. Anyways, and you can see that this game does not have any stable. Based on the starting point, you may end up not converging at all. Interesting. Very interesting. Okay, let's drink some water, get back to Andrew Ng. Yeah, you don't need to find papers every time. Use your brain first. Give yourself an opportunity first. Amir, I'm telling you, Amir, I'm talking to you. And I am talking to all of our supporters here and mental masturbators and armchair theorists. First, give yourself a chance to see. And if you solve it like this, it just boosts your confidence that I can think on a thing, think on a problem and solve it. I have the ability to think. That's super important. I don't need to ask other people all the time. I don't need to read the paper. I don't need to ask ChatGPT all the time. And once you do that, your mental power, thinking power increases as well. Your believing, your thinking power increases. Standing ovation. Standing ovation. Woo!
For the log likelihood. And this lower bound, this green curve, has two properties. One is it is a lower bound, so everywhere you look, over all values of theta, the green curve lies below the blue curve, so it is a lower bound. And the second property that the green curve has is that it is equal to the blue curve at the current value of theta. Okay. So what the E step does, which we'll see later, and just keep this picture in mind as we go through the E step and the M step, is it'll construct a lower bound that looks like this, right? Oh, and also to foreshadow part of the derivation, right? There was that addendum to Jensen's inequality where we said, well, under these conditions, it holds with equality, right? E of f of x equals f of e of x. We said, well, the two things are equal under certain conditions. We want things to be equal. We want the green curve to be equal to the blue curve at the O value of theta. So we'll use that addendum to Jensen's inequality when we derive that. So that's E step, is draw the green curve. And then what the M step does is it takes a green curve and it finds the maximum. Sorry, still drawing the green. What the M step does is it takes a green curve and it finds the maximum. And one step of EM will then move theta from this green value to this red value. Okay? So the E step constructs a green curve, and the M step
I liked it. Even
finds
the
maximum
previous
of the green
session,
curve.
you can see that,
And
dude, this creativity transforms from thesis playlist to Andrew NG playlist and machine learning. I am in my creative mode.
One
now.
iteration of EM. The second iteration of EM, now that you're at this red
Bro, it's
thing,
getting warm.
is we'll construct a new lower bound. And again, it's a different lower bound. Everywhere the red curve is below the blue curve, and the values are equal at this new value. That's an E step, and then M step will maximize this red curve, and so on. Now you're here, construct another thing, do that, right? And you can kind of tell that as you keep running EM, this is constantly trying to increase L of theta, trying to increase the log likelihood until it converges to local optima. Okay. The EM algorithm does converge only to local optima, so if there was another even bigger thing there, then it may never find its way over to that other better optimum. But the EM algorithm, by repeatedly doing this, will hopefully converge to a pretty good local optimum. Okay? All right. So, let's write down how we do that. Let me think. I should use the new board. No, it is okay. All right. So I've already said that our goal is to find the parameters theta, then maximize this. And so that equation we said just now is sum over I log sum over Zi P of Xi comma Zi.
Wait a second. Why are we using
Okay, so this is
I
just
don't
what we
get it.
had written down, I guess.
When are we, like, where are we using gen? Logarithm
What I'm
of
going to do
P
next
with
is
convex?
divide by
Is that it? What is this QI function?
multiply and divide by
Does
this.
it come from the k-means? Dude, I understood k-means, I
Um,
understood Jensen, but now
Where Qi of
doesn't mean
Ci
if you know them separately, you
is a
know the
probability
combination. Big life lessons, guys. Q function. I don't even know where Q function is coming from.
i.e. sum over Zi Qi of Zi equals 1. So I'm going to multiply and divide by some Fourier distribution. And we'll decide later.
So if you know
how to
algebra,
come
you
up
know
with this Fourier distribution.
topology. It doesn't
But
mean you
yeah,
know
I'm allowed
algebraic
to
topology.
construct a Fourier distribution and multiply and divide by the same thing. Now,
If you know
if you look at this, let's put square brackets
how
here.
to make a,
If these QIs, if this is a Fourier
fucking-
distribution, meaning that some
you know
of
how
the
to
QI,
plant a
Ci
tree,
sums
if you
over
know how
sums of
to,
1, then this thing inside is
what
equal
else?
to
How can I mix tree
sum
and
over
something
I
else?
log of an expected value of
Plant a
Ci
tree.
drawn from the QI distribution.
If you know how to plant a tree, if you know how to make a tree house, it doesn't mean you. Okay, tree house is at. Oh, okay, that's it.
Goodbye.
If you know how to plant a tree, and if you know how to make a house, it doesn't mean
Use
that you
colors
can
like
make
this.
a tree house. What else? If you know how to work with machines, if you know how to learn, it doesn't
So
mean
the way
that you know
compute the
machine
expected
learning.
value of
Makes
you
complete
know, some
sense.
function of Zi is
Um,
you sum
what
over all
else?
possible values of Zi of the probability of Zi times whatever that function
Trash
is.
can.
So
If you
this
throw away
equation is
trash,
just
if
the
you have a
expected
can at
value
home,
with
it
respect to
doesn't
Ci
mean you
drawn
have a
from that
trash can.
QI distribution of that thing in the square brackets.
What
in
else?
the purple square brackets.
If you are white, if you have a board, it doesn't mean it is
No.
white board.
Using the
The same for blackboard.
concave form of Jensen's inequality,
What else?
we have that
If you are a top,
this is greater than or equal to
if you have lap, it doesn't mean you are a laptop.
oops,
What else? tablet. No. If you are, if you have back, if you have a thick back, and you are part of a pack, it doesn't mean you have a backpack.
So this is a form of Jensen's equality where
What else?
f of e x
Oh my God.
is greater than
So
or
it's
equal
very
to
obvious.
e
Very
of
obvious.
x.
These are obvious
where
facts
here,
of life.
This is the logarithmic function, right? So the log function is a concave
If your
function,
name
it
is
looks like that.
Saravi, doesn't
And
mean
so,
you're from Sari, you're from
using
Amol.
the, I guess, yeah, using the form of Jensen's equality with the signs reverse, right? F of ex is greater than or equal to e of fx, so you get log of expectation is greater
If
than
you
or equal to
have-
expectation of the log.
If you have a camera, if you're a man, it doesn't mean you are a
And
cameraman.
then finally, let me just take this expectation and unpack it one more time. So this is now
What
sum
else?
of I, sum of zi,
Anyway,
so I just took this expected value
Enough.
and turned it back into sum of random
enough.
variable.
The rest on you. Go learn it
Times
yourself. Comment below whatever comes to your mind.
So, if you remember this picture from the middle, what we wanted to do was to construct a function, construct this green curve, there's a lower bound for the blue curve.
If your car has
And
wheels and if your
If
car
you
has
view
chair,
this formula here
it doesn't mean your
as
car
a
is
function
a
of
wheelchair.
theta, right? So your x is just your data, and
Well,
z is a
actually, kind
variable
of
you
is.
sum over. So this whole thing is a function of theta, right? Because the x's are fixed, z is just something you sum over. So this whole formula here, this is a function of
If
the
you are
parameters theta. And what we're showing is that
If
this
you are
thing,
dumb and if you have a bell, it doesn't
this
mean you are a
formula here,
dumbbell.
this is a lower bound for the log likelihood. For-
Kettlebell the
for
same
this thing.
way.
Right, I guess this is L of theta. So, go ahead.
If you can, that is very
Oh,
important.
how to
Actually,
discipline?
that is the most
Sure.
beautiful one. If you can kick and if you
So-
can punch, or punch, it doesn't mean you are a kickboxer. Kickboxer needs more
Let's see.
synergy
Let's go
between
see
your
this.
hands and kicks.
Uh,
So if you go study Taekwondo
let's say that
and you
Z
go
takes on
study
values from
boxing
1 to
for a
5,
long
and
time,
let's say Z
it
takes on
doesn't
values
mean
from 1 to
that
10,
you
zero to
can
10
be the
sacrifice.
kickboxer.
and I want
This
to
is two
compute,
different. We have a
the
lot of
expected value
combos
of,
that are mixing kicks
some function
and
of some
punches.
function g of z.
Oh my God, this is so.
Then the expected value of g of z
Amazing.
is sum of all the possible values of z, of the probability that you get that z, times g of z, right? So that's what the expected value is of a function of a random variable, right? And
Actually,
this is-
the
and
one that you
expected
throw
value of
and
z
then
is
you kick
sum over z
right away after
P of
it
z
closes this
times z,
half
right? That's the
plane
average
here.
random variable.
It's very
And so,
common. Kamaru
in the
Usman
notation that we have,
got
the probability
knocked out
of z
the same
taking
way.
on different values is denoted by
Uh,
qi of z.
so
which is
this
what we
is
want
shows
up.
that it's not boxing and
Does it make sense?
taekwondo and kicking.
Yeah, does
It is
okay?
kickboxing. Kickboxing kicking actually. KBK
Right, if one of these steps
and
doesn't make
B
sense, then-
and sometimes KKB, KBBK. That's it. We can combine.
Okay.
If you go
Alright.
CrossFit, if you are Christian and wearing a cross, and if you're fit, it doesn't mean you go CrossFit. You may go some other sports.
Now, one of the things we want when constructing this green lower bound is we want that green lower bound to be equal to the blue function at this point, right? And this is actually how you guarantee
I
that when you
didn't
optimize the
pay
green function by
fucking
improving on the green
attention to
function, you're
this.
improving on the blue function. So we want this lower bound to be
part
tight,
of the
right?
video.
The two functions be equal, tangent to each other. So in other words, we want this inequality to hold with equality. So we want
If you are,
yeah, so we want the left-hand side and the right-hand
if
side
your
to be
name
equal
is Steve and you have a
for
job, it doesn't mean
the
you are a
current
Steve
value
Jobs.
of theta.
What else? If you have an eye and you have a phone, it doesn't mean you have an iPhone. You may have Samsung.
So on a given iteration,
Okay, I got it. I perfected this game. Enough. I'm tired of it now.
EM, with the current
I
parameters
will say goodbye to this game at my prime.
equal to theta, we want
Ba-da-ba-da-bang.
we want,
Thoughts,
I know
thoughts
this was a
keep
long
coming
map,
to my
but
brain
yeah,
because
we want
I'm
the
not
left and
paying
right hand
attention
sides to be
to
equal to
this.
each other.
What is Q?
Because that's what it
Q
means
was
for,
the fucking weight.
Uh,
It's not very important.
for the lower bound to be tight. for the
K
green
means-
curve to be
Q comes
exactly
from K
touching the blue
means-
curve as we construct that lower bound. And
So the whole
for this to be true,
thing was that we can prove that K-mean converges using Jensen inequality.
we need the random variable inside to be a constant. So we need P of xi, zi, divided by qi
Let's
of
go
zi
text it.
to be equal to a constant. Right? Meaning that no matter what value of zi you plug in, this should evaluate to the same value. In other words, the ratio between the numerator and denominator must be the same. And fortunately, so far, we've not yet specified how we choose this distribution for zi. Right? So far, the only constraint we have is that qi has been a probability density has been a probability distribution
Hussein's
over zi.
are, right?
You can choose whatever distribution you want for zi. And it turns out that we can set qi of zi to be proportional to p of xi zi parameterized by theta. And this means that for any value of z, so z indicates is it from Gaussian 1 to Gaussian 2, right? So this means that the chance of Gaussian 1 is proportional to the chance of Gaussian 1 versus Gaussian 2. Whether zi takes on 1 or 2 is proportional to this. And I don't want to prove it, but one way to ensure this, and this is proven in the lecture notes, but it turns out that one way to ensure, so the QIs need to sum to 1. So one way to ensure that this is proportional to the right-hand side is to just take the right-hand side. Sorry. So let's see. Right, so the QIs have to sum to 1.
I don't know what
And
the
so
fuck
one
is
way
QI.
to ensure the
Okay,
proportionality
QI is the
is to just take the right-hand
weight.
side
Why is it QI of ZI? Isn't it QI of ZJ?
and
I
normalize
thought
it
QI is the weight
to
that
sum to 1.
point ZI belongs to the distribution I. Anyways, you have to finish.
And
Dude,
after
I
a
don't
couple
care.
steps
Actually,
that
I
the
just
lecture
want to
notes, I
finish
don't know what
this.
to do here.
I don't care about the quality of finishing. We had a
You can show
productive
that this
session.
results in setting QI
I
of CI to be
dealt
equal
with
to that,
one of the problems that I had in my mind for a long time, and I was thinking, oh my god,
And
that's
so,
so amazing. That's such
sorry,
a
I skipped a couple steps
stable
here.
Nash equilibrium.
Different
Bullshit. It was
lecture notes,
bullshit.
but,
Just write it
turns
down.
out that if
Don't
you
keep
want
this
to be
stuff in your
constant,
fucking
meaning whether you
brain.
plug in zi equals 1 or zi equals 2 or whatever, this
These
evaluates the
ideas are
constant.
bullshit.
The only way to do
And
that
some
is
of them
to
are
show
good,
that
but you don't know
numerator
if
and
they are
denominator proportional
sometimes
to each other.
Malakia, sometimes
And
good.
because
So you
QI
don't know
of
when
CI
it is
density
Malakia,
is sum to
sometimes when
1,
it is good,
one way to
unless
ensure the
you
proportional
put it
is
on
to
the
just set
fucking
this to be right-hand
paper.
side and normalize the sum to 1. Okay? And we derive this a little bit more carefully in the lecture notes. So, just to summarize, this gives us the EM algorithm. Let's take all this, everything we just did and wrap into the EM algorithm. In the E step, we're going to set Qi of Zi.
Next time, I will get involved and will ask ChatGPT. This time I was so all over the
Equals
place.
to that. And previously, this was the Wij's, right? So so previously we're storing these probabilities in the variables we call Wij's. And then in the M step, we're going to take that lower bound that we constructed, which is this function.
Wow, dude, that white cloud, that big white cloud, now it took over all the space. Fuck, I didn't notice it.
And maximize it. with
Now
respect
we
to
have
theta.
only a bit of blue over there.
And so remember, in the M step, we constructed this thing on the right-hand side as a lower bound for the log likelihood. And so for the fixed value of Q, you can maximize this with respect to theta, and that updates.
Fuck off, get the fuck
theta.
out of my face,
Maximizing the green
Andrew.
lower bound, right? That's what the M
I
step
love him, but
does.
he's
And
really
if you
annoying
iterate these
today.
two steps, then you find that this should converge to a local optimum. Okay. Oh, and just maybe that's the obvious question. Why don't we try to maximize, right, theta? Why don't we try to maximize the log likelihood directly? It turns out that if you take the mixture of Gaussian's model, try to take derivatives of this and set derivatives equal to 0, there's no known way to solve for the value of theta to maximize the log likelihood. But you find that for the mixture of Gaussian's model and for many models, including factor analysis, which we talked about on Wednesday, if you actually plug in the Gaussian density, if you actually plug in the mixture of Gaussian's model for P, and take derivatives, set derivatives equals 0 and solve, you will be able to find an analytic solution to maximize this M step, and it'll be exactly what we worked out in the early derivation of the EM algorithm. Okay, but so this derivation shows that the EM algorithm, is a maximum likelihood estimation algorithm with optimization solved by constructing lower bounds and optimizing lower bounds. Okay, all right. That's it for today, and only stuff up to here, right? And so this stuff will be up to the midterm, but we'll talk about on factor analysis. We're not on Wednesday. We're not in the midterm. Okay, so let's break for today, and I'll see you guys on Wednesday.
Perfect. Ah, fuck yeah. Done. I say 1.5. 1.5. This time, just 1.5. Counter. Honestly, 1.5. I'm not playing more. Because at the end it got boring. I just lost my connection to the course. And I didn't get the necessity. Okay, Jensen fucking inequality. I think I need to. Do you like it this way more or this way more? This is not bad. Let's play this mode. Go, bro, go. One and a half. Honestly, this is the half. The next one is 1. Okay, this is actually better. Map vote end. I've never seen this situation. Oh, I got into the game right the moment it got finished. That must be it. So probably our 1.5 will be 2. That is what it is. Oh shit. It'll disappear. Let's go. Latin? What? Latin language? Shit. We are good. Okay, okay. We cannot act very wild here. So let's go. We are together in this. Latin language lizard. That's such a lengthy name. Bro, come on! Okay, they are so good. Definitely are 1.5. Where are you? Drop dead. Oh. Again, Latin language is there. Where are you? Bro. Okay. Bro, you better kill somebody. Where are you? Are you here? Who are you shooting? Oof, killed. Oh. Why should your name be freaking beautiful? Wow, he got that snipe. That's a legit. And we have a guy who has that too. He owes. Okay, bro. Where is he? Where is he that shooting? Ah. Okay, we better act. Normal. Dude, I killed him. What are you talking about? Bro, sometimes it's unfair. Wow. You got the knife? All of my friends have like clothing. That's interesting. They were very good. Okay, I will do this. I'm down with the pool, but well, the game has a limit. You cannot kill like 40 people because obvious reason. Oh, so chickens get out of these boxes. They are chicken boxes. Interesting. Bro, I killed him 10 times. Sometimes you see stuff. What a nice shot. Ah, no, 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 he kills me. Where are they? Come on. That's so fucking. Oh my god, this game is getting crazy. Dude, I killed him! Bro. That was very exciting. That was genuinely exciting. Oh, motherfucker. Fuck. Oof, killed them right. Oof, I killed them so good. Ah, dude. I was about to escape. Dude, what if we go downstairs? Actually, a lot of them go downstairs, so... Check my facial expression there. 3 chickens. What are you doing? Chickens? Bro, this motherfucker comes to kill me. Oh shit, bro. Stop. Oh, this motherfucker is here. Ha ha ha. Why are they downstairs? What brings them downstairs? Oof. What a kill. Professional. Oof. Honestly, I hit his face. I could see that my bullet on his fucking face. Fuck face. Wait, where are you? Bro, give us something. Oof, killed nice. Oof, ah. Oof, killed nice. Oh, don't kill me. Oof, killed. Nice. Focus on one, dude. Focus on one. Dude, I killed. Dude, I have a machine gun. Bro, I killed. Like, fucking shoot it. Fuck yeah. Thanks for coming here. This bullet was so strong. Did you feel it? Wow, he's so... It's always him winning, it's never us. I killed. Okay. Fuck you, I killed you. Disgusting rat. Fell downstairs. Nice kill. Where are you? Who are you? Upstairs, okay. Okay, it was the first, okay, done. I'm happy. Okay, I'm out. What's happening? What's going on? What's popping? That's it, I'm gonna go eat lunch. And then maybe some Gaussian. Should I go kickboxing today? Let me check the kickboxing group. Guys, I don't know anything about Bitcoin. So TJ said we have a session today. But it is at 7, so fuck. I don't want to eat my lunch at 6 and go to the kickboxing club at 7. That's what we are going to do. I'm not gonna eat lunch. I come back home and eat dinner. Dinner and lunch. Whatever. It's a lunch. Have a good day, guys. 1:50. Let's stay 10 seconds with each other and it turns 1:59. 5, 4, 3, 2, 1.